Hello everyone, my name is Roy Jafari and I would like to welcome you to another video. In this video, as this suggests, we are going to look at a paradigm shift from statistical soundness to computationally measuring usefulness. And there is a lot here to unpack with this name, and we're just gonna see how we used to make sure that our statistical models are any good and they are doing what we want them to do, towards how basically data mining and machine learning are making sure that the models or the predictions that are happening using those techniques are any good. So we're going to sort of see this transition from statistical soundness towards computationally measuring usefulness and see what all of that means. All right, let's look at the slides. All right, so here we are going to start by sort of talking about what's a model and what's an analytic model. And after we understand what we mean by model, we're going to sort of see how we used to make sure that our statistical model are sound or only good. So then after that, we're going to see how now are things done, and to understand the difference between them. And then of course we're going to look at a couple of methodology that we use for this new way of making sure that our models are well created and are doing what we need them to do. And of course we're going to talk about some metrics and tools that are used along the way for making sure that the prediction model and classification models are evaluated. All right, so what's a model? A model is a simple representation of reality. And of course, the reality has many details and delicacies and ups and downs, depth and peaks and valleys. There are so many things about the reality that if we were to have a model, an accurate model of the reality, we would have to have the reality itself. So every time we have a model, we are making sure that we have a simplified version of it. I mean, the best example of a model of a reality that we've all used is a map, right? If you have the map of the world, it has a gross estimate of where everything is, right? So that, for those specific purposes that we have the map of the world, is very useful. So we have it, even though it's very simple, it's useful, so we use it. So this, how much detail do we want to include in a map is sort of an art based on how we're going to use that map or how we're going to use that model. So let me talk about what George Box says about this phenomenal model, which is very interesting and is very relevant to our discussion today. George Box says, essentially, all models are wrong, but some are useful. So why George Box thinks all models are wrong? Why all models are wrong? It's because of that simplicity of the reality we said. I mean, the models are sort of like a simple version of the reality. So we cannot have everything of the reality in the model. Because of that simplification, what George Box means, all models are wrong. At the same time, we also have to understand, how do we really simplify reality? And the answer specifically for the data analytic models are we make assumptions. Some of these assumptions are implicit and some of these assumptions are explicit. It doesn't matter if our assumptions are implicit or explicit. Whenever there is an assumption, there is some simplification, and because of those simplification, the model is wrong. So the next question we want to answer is, what is a data analytic model? Basically, as the sentence here suggests, a collection of assumptions about the underlying patterns and relationship in a data set is a data analytic model. But data analytic models serve some purposes. These are those purposes. We've got descriptive purposes, we do visualization, we come to table to give us some information. We might be doing predictive models that we've been doing in the past couple of videos, and also we might be able to do some prescriptive model that we will see in one of the future videos what we mean by that. So, when we have data analytic models that, we want to make sure to sort of see how they're doing, we used to do this in a statistical way. We used to follow models guidelines. So for example, in the past couple of videos, we've been looking at how we would go about using regression, linear regression, and logistic regression to do binary classification and some predictions. And all of these models come with a lot of guidelines. We actually skipped through some of them. I mean, these guidelines are such as you have to make sure that there is actually a linear relationship between your independent and dependent attributes. And you would have to actually check about the multivariate normality and multicollinearity and also homoscedasticity. I don't want to get into the details of what these are, but I'm just saying that, if we wanted to be absolutely correct when we use linear regression, we, had to actually make sure these criteria are met before we actually can rely on the results of linear regression. So this is sort of the model guidelines. At the same time, we look at the significance levels of the model. We also look at the significance levels of all of our independent attributes, coefficient. So all of those things are, sort of like a procedural way that you have to do for that specific model that we used to do in a statistical model. But here, when we move towards data mining, we have a new paradigm. And that paradigm is we computationally measure usefulness, right? We just measure how useful this model is. And if we manage to do that, then we can actually sort of like rid ourselves of those guidelines and the extra things that we have to pay attention to. We only can apply these computationally measuring usefulness if, and that's a big if we have meaningful, relevant, and measurable performance metrics. I mean, that meaningful, measurable, and relevant performance metrics is not available all the time. But if we do have such metric, if, and that's a big if, and unfortunately, most of the time, we have a metric, but it's not relevant completely or meaningful. And because it's measurable, we use it, and that's called proxy. And that is actually where a lot of the concerns of ethical aspects of machine learning and data mining comes into place. So that's some part of that, but that's just kind of like a tangent here. But if we have that, then we can sort of like measure that instead of having to make sure everything about our model is working. If our metric that captures usefulness is improving, so we're gonna have it, we're gonna want it, right? But like I said, it depends on if we have that metric. So there are two methods that we can do this. We can go about actually calculating this. Actually go about calculating this, and one of them is the holdout mechanism. In the holdout mechanism, what we do, we separate the data into train set and the test set, and we use the train set to train our model. Train set, train our model, and then we don't use the test set. The test set is the fresh data that our model has never seen, and then we test our data on the model on the test set. And if our model, which has never seen the test set, does a good job in predicting the test, or at least does a better job of whatever method we used to use, right? So then it's a success, and we say, okay, we have evidence that whatever this model is doing well, or is actually at least doing better. So let's take an example. In this example, we have used a linear regression to calculate the performance of students. So it's a student performance based on 4 independent attributes: the travel time, study time, free time, and the go out time of the students. And if we apply the whole data, this is what we get. These are the estimate beta that we get. But instead of doing that, we separate the data into two parts, the train set and the test set. We use 20% of the data for the test set, so we only use the train set, right, to only use the train set to come up with these estimations. Pay attention that these betas are a little bit different, right? Pay attention. For example, look at this number. These betas are a little bit different. So now that we have estimated these betas, now we can sort of check or run these in test set by the model to see what's the prediction. Pay attention here, we've never used this data before, and we are going to use what we learned from here to predict these values. Therefore, what we have here is a good way to make sure our model is actually doing any good prediction, right? So that's the holdout mechanism. Pay attention, I kind of say it, but to just emphasize, we did not use this data at any point in our prediction. These numbers are completely fresh, and we are using the knowledge we are capturing from here to be able to predict those. And that's the whole sort of like a holdout mechanism. That's how that methodology works. So we get to this point that we have a column of actual values, and we have a column of predicted. Of course, we can look at these values, say, okay, 11, 13.4, there is 2, sort of like error, 12, 14, another 2, 18. So we can sort of like go through these and look at them by one. That's one way we can eyeball them. But are there any other method? Imagine we've got like 2,000 of them. Do you really want to eyeball everything? Are there other methods that we can use here to help us? One way we can go about this is use a visualization. We use a heat map to sort of like put the errors of a random predictor, meaning that it just every time it wants to do a prediction for the member of the test set, it just comes up with a random number between the minimum and maximum of the test set, minimum and maximum of the dependent attribute. And then also with the mean, another predictor, we assume that there is a predictor that every time it wants to predict something, it uses the mean of the dependent attribute. So then we have our model. So we sort of like visualize the amount of error of each of these three models. So these are the three models that we have. This is the model we are interested in. This is the model we're interested in. We compare that with those ones, right? If we don't have any other models to go about prediction, our best bet would be to predict that the average is going to happen, right? But if we were to use this model, whatever it is, for whatever application this is an example from another application. If we were going to use this model, we're going to do much better than the mean. We're going to have less error. So that's how we would go about using visualization. But how about being able to summarize or capture this performance by a number, right? Just come to a number that we can say, okay, this was the metric for this performance, and this is the same metric for another model. So we can see how well we have done. So now we're going to learn about three of those metrics. The first one is mean absolute error, and this is the formula. So we have the actual number minus the predicted value, and you have the absolute value of that, and then you sum all of the members of the test set, right? So that's what you have, and then divided by n. Mean absolute error. And the sort of like a Excel calculation of that is here. You calculate the absolute between these values, you say the absolute, and then you calculate the average of them, and that's how you would get the mean absolute error. Then you have mean absolute error, mean absolute percent error. The only difference is you have a denominator of the actual value here to sort of like scale the errors. If there is a large data and you have a larger error for it, right? It's more okay than if you have small data and the error is not as large as that, but it's twice as big as the value itself, right? So you sort of like scale the error based on the actual value of whatever it was that you were trying to predict. So that can help us with sort of like coming to a percentage value instead of a large number. It's something that we'll see in one of the slides, next slide. And then we've got, and this is the way you would go about calculating in Excel. So you have the absolute values, and then you divide that by the actual value, and then you calculate the average of all of these, and that's how you would go about this in Excel. And then you've got root mean square error, and this is the formula. You calculate the difference between actual and predicted for every value, power it to 2, and then you sum up all of those terms divided by n, and that's what we know as root mean square error. And that is how you would go about calculating that in Excel. All right, so these 3 metrics that can be used for capturing the performance of a prediction model have some sort of like quirks and behaviors that when you want to choose one of them, or when you look at the performance of a model and compare it with another model using one of these metrics, you want to know about that. First thing is, MAPE is the one that puts more weight on the repetition of error. Right? It means that if you sort of like have an acceptable prediction, meaning it's not off by more than 2, so that's sort of an acceptable prediction. And if you have a prediction that is really good for some but it's not acceptable for others, then if you were to go with MAPE, that would be sort of like, if what you are looking for is having more acceptable prediction, probably MAPE is better. But if what matters for you is, the collective amount of error, you want to be less. So if it's okay for you that, you have more repetition, but it's not okay for you to have the largest collective amount of errors, and that's when you would go with RMSE. Pay attention here. MAPE is excellent, and in terms of it being sort of like confined, it cannot be larger than 100%. When it's close to 100%, when it's 100%, it means you've been wrong so badly, like 100% could have been wrong, you're wrong, right? So if it's closer to 0, it means it's better. If it's larger than that, it means that it's not so good. But it's contained. It's between 0 and 100. But RMSE and MAE, you cannot say that. I mean, it can be as large as possible. And then all of them are indifferent to the direction of errors. That means that, if you have all of your errors are larger than your predicted value or smaller than the predicted value, because we've used absolute value here, and you're powering it to 2, everything is indifferent. I mean, it doesn't matter if it's larger or smaller. And then the MAPE is also not insensitive to the number of cases, which is great. I mean, if you have 100 prediction, if you have 100,000 prediction, so it's still going to be between 0 and 100%, right? But if you have with RMSE or MAE, if you've got 100 predictions, especially RMSE, if you've got 100 prediction, your number is going to be very different than if you've got 100,000 prediction. And that's what we mean by it's insensitive to the number of cases. And of course, because it scales the amount of error, MAPE, something that RMSE doesn't, then it's insensitive to the outliers. If your data or your tracer has outliers, every value there is like 1, 2, 3, around that number, and then there is just one out of, like, I don't know, 100. There's like a million, right? So if you are off by 500,000 and you're using RMSE, because that outlier exists, the other errors could have been just 2 or 1. They don't really matter at all, right? Because of that outlier. But with MAPE, that is going to be scaled. The small error is going to be scaled, and the large error for the outlier also is going to be scaled. So these are the things that you want to learn. Whenever you want to use one of these, I probably gonna want to use between RMSE and MAPE, because these are the ones that have more advantages. You want to pay attention. You want to sort of weigh the advantage of RMSE, which is the magnitude of errors, which is sometimes that's what you want, with the other advantages of the MAPE. So this is basically what you want to get from this slide. All right, let's move on. So what we've been sort of talking about here, it's been the cases of us having, prediction model, right? Those were value here, right? If we go back to this slide, do you see these are all value, right? So these are all like numbers. But what if we have a classification case? This is a classification case. You have either pass or fail for your actual student performance and also for your predicted student performance. So this is a classification. How do we capture the performance visually and with a metric when we have a classification? So that's something what we did for prediction, we want to do for classification. One thing we can use is a contingency table. That contingency table is basically us counting the number of cases that we've got on the combination of the actual and prediction. So for example, we have 6 cases here that we've got actually pass, and we've also correctly predicted pass. So we've got 1, 2, 3, 4, 5, and 6, right? So this is those 6. And then how many do we have that is, correctly, we have calculated correctly at the actual fail, and it was actually failed too. So we're looking for fail, which is this one. There's only one of them, so these are those. And then let me change the color of my. All right. So we've got predicted pass. We predicted pass, but it's failed. So there is one here, and there is another here. So these are those 2. And eventually we predicted failed, but it was actually a pass. And this is that one, right? So when you have a contingency table, you want the diagonal on this side to be, have more numbers. You want these to be 0. You want the green ones to be larger, as large as they can be. Of course, a perfect classification would look like this. A perfect classification in this example would look like this, right? It would be 8, 0, 2, 0, right? So that would be the perfect classification. That would be what you want to happen. This is an example of binary classification, but you can actually use it for non-binary classification to contingency table. This is an example here. These are what you want to be higher, so you can actually calculate the accuracy by summing those up divided by the number of cases, or you want calculate the error rate by summing everything else up and divided by the number of cases. So that was the way we would go about that visually, but how about if we wanted to capture that with a number? So there are 3 metrics we can use for classification: number of misclassifications, accuracy, and the error rate. So let's go ahead and calculate these for this example. So here the number of classification, number of misclassification is 2 out of 10 cases, right? Our accuracy is the number of correct classification, which was 8 divided by 10. So we've got 80% accuracy. And our error rate is 1 minus accuracy, which is 20%. So these are the 3 metrics we can use for classification. One of the things that is very important for us to understand is, as easy as the holdout mechanism looked, it has a weakness. And I'm just gonna sort of like don't rob you of this opportunity to think about this. What that weakness could be, because it's a very important and delicate weakness. So why don't you participate in the conversation and discussion here, and in the comment let us know what is that weakness, and of course after a while I'm going to provide the answer there too. All right, so the next method or the next methodology we're going to learn doesn't have that weakness. So you might want to use sort of like see where we went from holdout mechanism to this next other things to maybe help you find an answer. Is k-fold cross-validation. You may stop the video and read this, but I think it's much better for me to talk in the visual here. So for example, with k-fold cross-validation, you can choose any k. K can be 2, 3, 4, any k. But normally you either choose 4, 5, or 10, or 3. So you don't want to like choose 20 or 100. It would be just too much. But what k-fold cross-validation is, let's look at the example of 4-fold cross-validation, meaning that we've chosen k as 4, right? So that's what it is. So this is k-fold, k is equal to 4. We separate the data into 4 equal segments, and then we give each of the segments an opportunity to be a test set. So we start from the first one. We use these 3 as a train set. So these are all collectively used as a train set, and this is a test set, and we calculate the performance on the test set. So we do this 4 times, and then we sort of like calculate the average of the performance on all of the test sets. In this way, all of the data in the data set, all of the data objects in the data set have had a chance to be tested, and that's great. So I'm not going to say more, so you are going to be able to answer the question that I raised earlier. So one last thing I would like to mention here before going to the last slide, which is a summary, is that binary classification, which is a very specific type of classification, have many more tools. Most of the time, actually, when we have a classification, it's a case of binary classification. So we're going to have a whole video just about, it might actually be 2 videos, just about the specific tools and metrics of binary classification. All right, so let me offer some summary here. In this video, we talked about what's a model, why do we have model, what is the analytic model, how do we make sure that the model is necessary. We talked about the usefulness of the model, and the fact that if a model is useful, it's when we want to use it, and we sort of use that to sort of show you that we moved from the statistical soundness toward being able to measure the usefulness in a metric. And that's what basically we learn here. We learn holdout mechanism, and also k-fold cross-validation, and also a bunch of different metrics and visualizations to capture the performance. Now we're starting to learn how we could go about actually computationally measure usefulness of our analytic models. Until the next video.